Previously on Level Up Double E Lab.
Well, as it turns out, the third time is a charm for me trying to make an RF preamplifier for my HF transmitter project. Yeah, I took that victory lap a little too early. As it turns out, there was a problem lurking with this RF preamp, and it came out in the worst way possible. Let's have a look at what happened. So I proceeded to do CW and single sideband testing on the complete rig with that amp installed when something happened we all dread when we're working on electronics. A sizzling sound followed by wisps of magic smoke and the screen going blank. Yeah, my troubleshooting turned up almost immediately that I'd fried those two 2N2222s, which was surprising because they were not getting alarmingly hot during the bench testing. So I did some more research and pretty quickly turned up that I experienced a classic BJT thermal runaway problem. Apparently, and I definitely overlooked this small but mighty detail, Class AB push-pull amps built from BJTs are apparently prone to thermal runaway if you don't properly account for the approximately 2 millivolts, I think it is, per degree C drop in the base to emitter voltage coefficient. So as they get hotter, it takes less and less voltage at the base to turn them on, so to speak. And I'm 100% confident that was the issue. So what I did was I replaced those two fried 2N2222s, and I got lucky, nothing else on the board was damaged. I powered up the repaired board and I monitored the idle current with no input signal going to it. So just the amp sitting there doing nothing. And sure enough, and I'll put the data on screen here, the idle current slowly creeps up over time. You can see that even after only about 5 minutes, the current crept up from 115 milliamps to almost 150 milliamps. Now, that value is all the stuff on the board, not just the 2N2222s, but that increase is 100% being caused by the 2N2222s. I did separate tests that confirmed that. Now, in hindsight, I had some early indication of this problem because when I was doing some key down and key up testing in CW mode, I was monitoring the amp current being drawn by that board, and I noticed that it was not returning to 115 milliamps. It was kind of stair-stepping, meaning that it was reaching a new and higher level after each short burst of power. I guess I was just too slow to figure it out before the transistors blew out. And in case you've never seen what a 2N2222 looks like when it releases that magic smoke, here's what it looks like. It's kind of subtle, but definitely noticeable when it goes bad. So this design sucks, but to be fair, I'm not throwing Harry Lythal under the bus here. I made changes to the design that he shows on his website, not the least of which is my choice of the output transistor and the value of the emitter resistors, both of which, as I now understand much better, can apparently have a huge impact on the thermal stability. So I guess more specifically, I should say it's my version of Harry's design that sucks. Fortunately, the fix is pretty easy and it has two elements to it. The first and probably the most important element is I need this diode right here, which is the one that sets the bias for the two 2N2222s, to be as close as I can get it to the temperature of those two transistors. That way, as the transistors heat up and their VBE values drop, so does the diode also heat up and its VBE equivalent, essentially its PN junction equivalent, correspondingly drops and therefore stays kind of synced and reduces the bias voltage and the transistors don't thermally run away. Classic negative feedback. And the second change is I need to thermally couple those two 2N2222s together so that it's harder for one to run away thermally from the other. And as a quick preview, I've made the changes to that amp. Here it is, already reinstalled. It works. Let's take a quick look at how I got there. I milled up this small piece from aluminum bar stock. I'll use it to join together the heat sinks on the two 2N2222s. That'll help a lot to keep them at the same temperature and will add more surface area and thermal mass. I've also machined this pocket that I sized to fit to the dimensions of the bias diode. Now that diode will be very closely thermally coupled to the two transistors. Assembly begins by first putting some thermal conductive grease in that pocket, then inserting the diode. I'm using a small piece of FR4 as a clamp. It's single-sided copper and I coated the foil with solder for better oxidation resistance. The depth of the pocket is just a little bit shallower than the diameter of the diode, so that there's a small bit of clamping force when the screw is tightened, but not enough to risk crushing or cracking the diode. Next up is attaching the two heat sinks to the sides of the block. I mashed their fins flat and then dremeled holes in their center so that I could screw them to the block. Of course, I used a bit of heat conductive grease between them and the block. And here's what the assembly looks like. It's a real kludge, that's for sure. I doubt anyone has ever gone to such great efforts before to heat sink a couple of TO92 transistors. But just in case this is inadequate, I've got this little fella here to attach in place of the FR4 board if I do need even more heat dissipation capacity. Before assembling it to the transistors, I added dabs of grease to them as well. Then it just presses into place with minimal force. And to make sure it stays in place, I added a wire tie just to complete the hideous ensemble. It's definitely not an industrial art masterpiece, but I think it's sound seat-of-the-pants thermal engineering. Alright, so before I put the RF preamp back in the chassis, I thought I'd do a few bench tests here just to make sure everything looks good. And I think I can say fairly confidently that I killed this thermal problem that I had, this thermal runaway issue. So what I've done, I've got the signal generator at the lower left-hand corner, kind of barely on screen, and above it I've got the multimeter that's showing me the current that the entire board is drawing. Here's the RF preamp board here in the vise. Now that current is everything on the board. It's the two N2222 push-pulls, plus the other two N3904s and other passives on there. So it seems to reach a steady state equilibrium around 120 milliamps, and that's fine. That's certainly well within what the LT Spice would have predicted. The meter in the middle, that's just monitoring the voltage across that diode. Again, that's a diode that I embedded in the aluminum block. And then the signalant in the background is showing me the voltage across a 50 ohm dummy load. And I can turn on a minus 10 dBm input signal here. The current jumps up to around 300 milliamps, and it does keep going up slowly because the transistors are continuing to conduct as the block heats up. But again, that's constant power, but you can see the voltage on the diodes started to drop a little bit. And of course, the steady state current, the big thing here, the steady state current is quickly returning back to about 120 milliamps, and it would not do that earlier. It would come back to a higher level, almost like a stair-step function, until finally it just burned out. It just went into complete thermal runaway. So this looks good. I'm going to proceed at this point to put the RF preamp board back in the chassis and continue my tests. Alright, before I get into the performance tests, I have two construction items to talk about. First up, I built the 20 meter and 15 meter low pass filters. And I designed and 3D printed custom holders for them. These make it easier to grip the filters during insertion and removal, and I included raised characters on them that I highlighted with a silver Sharpie to make identification easier. Performance-wise, the 40 meter version checks out great on the Nano VNA. The 20 meter and 15 meter versions are acceptable, but they both have more insertion losses than I want at the high ends of their bands. 20 meters is especially concerning, so I'm likely to tweak them in the future to reduce that insertion loss. Next, I ended up having to add 12 dB of attenuation right here, between the SI5351 CW carrier clock and the input to the IF amplifier. Earlier I showed this attenuator on my block diagram, and I designed in a pad just in case I needed it. You can see it here on the schematic. But when I built that board, I temporarily put in a 0 ohm resistor just to get it running, and naturally I completely forgot about it. That is until I started doing the spurious emissions testing. I discovered very quickly that I was driving the living snot out of poor Q1. The signal coming out of the SI5351 was way too strong, even with the clock current dialed down to just 2 milliamps. That excessive drive was overdriving the rest of the IF chain to the point that Q3 was performing more like a Class C amplifier instead of Class A, which of course was pushing a bunch of strong harmonics into the second mixer. I'll talk more about that when I get to the spurious emissions testing. So I temporarily inserted a step attenuator in between the SI5351 and the IF input, and I found out pretty quickly that 12 dB was good enough to drop the drive level low enough to get the spurs under control. Unfortunately, removing that IF board to populate the pad would require a major tear-up of the rig to get to it. So instead, I whipped up this quick board and stuffed it with through-hole resistors to make up a 12 dB pad. Here it is installed to the top of the mic, modulator, and second mixer stack with the coax input from the SI5351 and the coax output routed to the IF board. Okay, finally the construction on the rig is finished and I can get on with the calibration and performance tests. Now the first calibration to do here is setting the bias on the RF final amp. And if you look closely at this next footage, you'll see that I recorded this before I blew up the RF preamp. Now the preamp has nothing to do with setting the bias on the final amp, so I just decided not to reshoot it. All right, I have installed the RF preamp into the rig. It's right here, no issues getting it in place. So the last thing I need to do before I can do trials on the rig is set the bias for the final amplifier. And I won't go through that in detail. Alan talks about it in depth on his channel for a very similar dual IRF 510 HF amplifier, but essentially it's setting the current that's going through the two FETs when there's no signal going through the amp. That's important because it puts the amp in the proper mode of operation. In this case, I'm trying to get it well into class AB and get as minimal amount of distortion, maximum amount of linearity that's possible. That's been well established for these IRF 510s to be 100 milliamps per FET. So to do that, I need to measure the current, and I put this jumper harness, or this bypass harness rather, so I'm taking the current that's coming out of the 28 volt power supply, running it through my multimeter in amps mode so I can see just how much current's being drawn. And before I started, I turned down the two adjustment potentiometers. There's one for each of the FETs. Turn them down so that there's no current going through the FETs. But there is a little bit of current. There's about 16 milliamps when I keyed the transmitter that's coming out of the voltage regulator and some of the other circuits to keep that voltage regulator in regulation. So start at 16 milliamps, key down, of course, turn up the pot on one of them till I get to about 116 milliamps. And then turn up the second one until I get to about 216 milliamps. And that's basically where I am right now. Of course, it's drifting a little bit as components warm up, but it's all set. It's ready to go. I do need to fabricate a little short piece of RG316 here to connect the output of the preamp into the input of the final amp, and then I'm good to go. All right, so I've installed the repaired RF preamp, but notice I'm still using the Keithley to keep an eye on it, just to make sure it stays stable through all the stress testing that I'm about to put the transmitter through. And speaking of the testing, the procedure that I'll be following here is paragraph 4.1 from the ARRL test procedures manual. It's output power test. And in this case, I'm only going to check CW mode. Now, the rest of the setup here, of course, I have to have a dummy load connected to the transmitter, which I do. And in between it and the transmitter, I have my 40 dB power tap so that I can take a small portion of that signal. And then that tap runs into the power meter on the left of the multimeter. And the multimeter itself is just recording the output of the power meter so I get a little more accurate reading. So here's what it looks like at 7.2 megahertz. So about 5.71 volts, that converts, as we can see on the chart that I'm showing on screen. It's just over 40 watts, actually close to 45 watts in the middle of the band. So that's really good for 40 meters. 20 meters is mostly 20 watts, and 15 meters is mostly 10 watts. Now, there's some roll-off on 20 and 15, and that's most likely due to that low-pass filter performance I mentioned earlier. In fact, I'm giving up almost 3 dB at 14.3 megahertz, and that's half the power. So I definitely have to go back and look at those low-pass filters and try to get that insertion loss improved quite a bit. So that'll be a future project. My original goal was to get somewhere between 20 and 30 watts, so I'm definitely overachieving on 40 meters, and until I fix those filter issues, I'm a little short on 15. And then lastly, I'd say I use those power meter readings from the multimeter, reading the power meter. And then also I used the multimeter to check the directional coupler voltage output, and then came up with a pretty easy linearization between those two data values to set a conversion constant in the Arduino software so I could get the bar graph to be as accurate as any bar graph can be. So I'll show a close-up of the screen now, and you can see I set the full scale to 50 watts, so that's pretty good. That gives me a little bit of headroom above the max power. So we're looking good here for the transmitter power. This next test I'm going to do is called spectral purity or spurious emissions testing. Again, it's from the ARRL Test Procedures Manuals, Test 4.4. And also, again, I'm only doing this on CW mode. And like it says, I'm looking for spurious emissions. That means products generated by my transmitter that are outside the intended transmission frequency. And generally, those are going to be harmonics created in the mixers or harmonics in the amplifier. And if they're too strong, they can cause unacceptable interference on other people's receptions. So the way I've got this set up, need a spectrum analyzer. And of course, I got my whole built SA right here hooked up to the usual Tektronix scope for the display. And you can't just run the output of the transmitter directly into the SA. That would be a very bad day for the SA. So I need to have some attenuation. In fact, quite a bit of attenuation. So to achieve that, I've got the 40 dB power tap that I've constructed on this channel. That's coming it's in line between the transmitter and the dummy load. And then out of that 40 dB tap, I've got another attenuator. In this case, it's a step attenuator. It looks kind of like this guy. This is an extra one I happen to have that I have not put the connectors on, but the one that I'm using has an input SMA and an output SMA. And again, that's between the power tap and the input of the SA. The rest of the setup, I got the SA set so that the top of the scale is at minus 20 dBm reference level. Now the procedure says to use minus 10, but minus 20 is perfectly fine here. I still have plenty of dynamic range. Let's talk quickly about some limitations. My SA only goes up to 70 megahertz. It's unlikely I'll have significant spurs above that, but I will be looking at the output of this transmitter later on my SDR to see if there's anything up in the higher frequencies of any concern, but really shouldn't expect to see anything outside the range of 70 megahertz. Now, what I've done before I start the test, I take that step attenuator and I set it to maximum attenuation. Then I key the transmitter and then I start selectively reducing or backing off on those attenuation steps until I get the fundamental pip is at the very top of the screen. That way I can use all of the dynamic range of the SA, which in my case is about 65 dB, and that would be from the top of the screen to the noise floor here. And that's plenty for this test that I'm doing because what I'm looking for are spurs that are non-compliant with the FCC requirement. And in this case, it's Part 97.307 subpart D, which applies to amateur radio equipment of this power and of this vintage, which says that all spurs must be at least 43 dB below the fundamental. So with that in mind, let me key the transmitter. Now, this is 40 meters. So this is 40 meters, and what I've done here is I pre-recorded the responses at 40 meters, 20 meters, and 15 meters. So let me zoom in now on the 40 meter results, and as we can see, they are compliant. So I've got one spur here below the 7 megahertz fundamental. It's minus 52 dB, and that's actually at 4 megahertz. That's the third harmonic of the IF frequency mixing with the VFO, I think, if I did my math right. And then there's two other spurs up frequency at the third and fifth harmonics, and those are definitely compliant as well. So no issues at all. 40 meters looks fine. So let's move on to 20 meters, and it's also compliant. We see a third harmonic here that's 50 dB down, so that's fine. Now, these two guys that are closely, very close proximity to the fundamental, those are at minus 49 and minus 53 dB down. Those are actually 6th and 8th order of the IF frequency, if you can believe it. And the frustrating part here is I cannot effectively filter those out because they're either barely in band or just barely out of band. So none of my filtering is going to be that sharp to pick those out. So I just have to live with them. But fortunately, they're compliant to the spec. However, going back to that problem I had earlier, I mentioned when I was overdriving the IF amp and had to put that 12 dB attenuator in there. Without that attenuator, they were much worse and were definitely not compliant with the FCC requirement, as you can see on screen here. So putting in that pad was an absolute necessity to stop overdriving that IF amp and get those spurs down. And then the last one is 15 meters. I'll show that on screen, and it's also compliant. So I'm 3 for 3 with meeting the FCC requirement here with this transmitter. I do have one spur right out here. It's probably the third harmonic. It's at minus 48 dB, and the rest are more than 50 dB down. So things look really good. I'm very happy with this performance. That's all I have for today. I did originally intend on finishing all the performance tests and integration with the receiver in this, what should have been the final episode on this project, but blowing up that RF preamp sent me back a little bit. So there'll be one more episode in this series. And in addition to showing the integration with the receiver, I'm planning on running a few more tests, including a two-tone IMD test to see just what the splatter looks like. I'm also going to attempt to measure the carrier suppression and the unwanted sideband suppression. And then also I've got a few ideas of how to look at the CW keying waveform and see just how rounded the edges of the dits and the DAWs are. So look for that and what should be the final episode on this series. I'm very anxious to get back to the George Collins collection that I showcased back in my 1000th subscriber episode. I've got several items in there that I'm just dying to get started on. So those will be some new projects coming up at the tail end of wrapping up this one. As always, I thank you very much for watching my channel and sticking with me in this lengthy series. If you do have questions or comments, please leave them below. So until next time, bye for now.